Welcome to week 2. So we're off to a great start today. We just spent 3 minutes of class time listening to Oasis, so that's not so bad. It's kind of, I'm amazed I'm allowed to do that. Anyway, I wish the speakers in here were better, but I'll file a complaint about that. All right, so today what we're going to do is we'll finish up what we were starting last time, which was using some standard Unix utilities to poke around under the hood of your computer and get a sense of what the operating system looks like from above. And that's kind of the first thing we're going to do in this class for a couple more lectures before diving into the details of how those things actually get implemented. And what we'll start today and probably finish next time is looking at file handles, which are important to understanding aspects of the process lifecycle. And then we're going to start talking about the 4 system calls that make up the process lifecycle. So this is a pretty important part of providing the process abstraction. This is the part of the kernel API that pretty much deals directly with how processes get created, how they run different programs, and then how they exit. All right. So a couple announcements. Today's the add drop deadline. There have been people who have been leaving the course, and I'm sad to see them go. But on the other hand, particularly if you're going to cheat, please drop the class today rather than do that. You will find yourself to be much happier, and the rest of your life will go a lot better. But in general, so to help you out with that, so we do have a website up now. If you go to the www.opsclass.org homepage, there's a calendar up, and more importantly, we've put up the text for assignment 0. So I'm going to come back to that. But if you are wondering whether the class is for you, assignment 0 is a reasonable place to start. I mean, it's not a graded assignment this year. There may be a few points at the very end of it that we haven't added yet. But in general, it just should give you some idea of what you're getting into, which is a large code base and a lot of good times. OK. The calendar is also up there, too. So we have a Google Calendar that we maintain for the class. It's embedded on the website. I would encourage you guys to add it to your own Google Calendars and start using Google Calendar if you don't already. The calendar is the canonical source of all information about office hours, which are starting this afternoon. I think we have office hours, Ali, at 4? OK, so the first office hours of the semester are today at 4 o'clock. The office hour schedule is still in flux a little bit, but please try, so if you are coming to campus or if you are around and you want to know if there are office hours, please try to check the calendar so that you don't show up and not find anybody there because somebody had to cancel or we changed things around. Probably starting end of this week, next week, we'll have a firm schedule that we'll use throughout the rest of the term. But during exam time, we pull some of the TAs off office hours they can grade, and people have cancellations and stuff like that. So please always check the calendar. OK. So in order to get onto the discourse forum, you guys need accounts, which I will set up this afternoon. I just need to figure out how to do that exactly. But once you guys receive an email with an account for the class, that's going to grant you access right now to 2 things that you're going to need. One is the discourse forum, which we're using as an alternative to Piazza, for those who have asked. That's discourse.opsclass.org. The other one is a private GitLab installation, which you can use to host private Git source repositories. So if you do not, you don't have to use the GitLab instance that we set up. The assignment has a description of other options for hosting private Git repositories. But I want to stress this. Your Git repository for this class, as is true for all of the coursework you do at UB, needs to be secured. So you cannot use GitHub to host a public repository and use that to collaborate with your partner. Later in the class, the submission tool will check whether your repository is public, and if it is, it will refuse to grade your assignments and probably send some incredibly nasty email to you and CC me. So it's really important that you guys have a private Git repository that you can use to collaborate with your partner. If you want to use our GitLab instance, that's fine. If you want to go to gitlab.com, that's fine. I think there's a couple of, so GitHub will provide you with a private repository. If you're a student, you can sign up, and I think you get like 5. Has anybody done that? Yeah, OK, so that's an option. I like GitHub a lot because the performance of GitHub is awesome. If you try gitlab.com, you may be sad because your pulls and pushes take a little longer than you want. But anyway, our GitLab installation is an option. It is not something you have to use. But again, your Git repository has to be private. The assignment is pretty clear about that. Okay, so maybe just a couple, sorry for all the administrivia. Later in the semester, we won't do this every day. So one of the things I want to stress very early on in the semester, particularly right around the time we drop the assignments, is I don't have a quota of A grades. It's not like they cost me money to hand out. It's not like anybody checks to see how many A's I give out. It's not like anybody cares. So I can give everybody in this room an A. And that would make me so happy, actually. I would be thrilled to do that. I have no need to curve you guys artificially into, whatever. I mean, if everybody in this class does the work to the level that I expect for an A grade, you will all get an A. Okay? Can I make that crystal clear? And again, that would be awesome. Now again, of course, you're thinking, well, I could just give you guys all A's, but then I wouldn't feel good about myself, right? And that's important to me. So you guys need to earn a grade of A. My old advisor, when I was at Harvard, we would talk about, oh, I got an A in a class, right? That's a weird phrase, right? That's like, again, like there was a limited number of A's and I managed to get one, right? My old advisor came from Berkeley with this weird phrase. He would say, make an A. And that sounded really weird to me at the time, but I think it's a better way to think about it. You are going to construct your grade for this class. If you want that grade to be an A, me and the course staff are going to do everything we can to help you. And again, there is no quota on the number of A's I can give out. It would be awesome if I could give everybody in this class an A mark and have that be meaningful, right? Have that mean something to the people that know about this class and know that if someone gets an A in it, they know how to do a certain set of things. If you have any questions about grading, please contact the course staff. This is a good time to do it. I will get the syllabus up on the webpage so that's clear about what the grading expectations are and things like that. But anyway, so please, our job is to try to get you guys to do well. I don't need to give out low grades just to make me feel like some of you learned and some of you didn't. I would prefer to everybody learn the material. Okay, so this year, the grading on the assignments is going to be a little bit different. In the past, the assignments are essentially the same, but in the past, there was like 50% of each assignment maybe that you could kind of get for free because they were things like code reading questions, right, that just require you to use like grep or something. So this year we took those out. So the points on the assignment are going to be for implementing things and getting them to work, okay? Now, here's the thing. Unfortunately, that's going to give some of you guys a false sense of frustration because you're going to be like, I've been working on this assignment for 2 weeks and I still have 0 points, right? Because you haven't gotten anything to work. The problem, so again, I'm not trying to discourage you guys, and the grading for the course is going to be will be changed to reflect how people do on the assignments. The problem in the past was that people would be like, oh, well, I already got a 50% on the assignment, so I'm okay. And they hadn't written a line of code. The code reading questions and the exercises that are in the assignments, while being ungraded, are really important. So please, I know you're all going to ignore me anyway, right? But whatever, I just feel like I should say it. Don't ignore them. When it says you might want to try the following things, please actually try to do those things. And if you have problems, come talk to the course staff because, for example, if you can't answer the assignment 0 code reading questions, you're going to have a very, very, very hard time later in the class. So these are designed to get you guys doing things that we know are critical to the success of the assignments, but we're just not going to grade them this year, right? So assignment 1, 2, 3, your grade is going to be determined by the code that you write and how well it works. Right? Any questions about this? Again, this is not intended to be mean or punitive or anything. It's just what we're trying to do is send you guys the right message about what we think is important. I don't care, and neither will Google, whether you can answer questions about code that they give you, right? Unless your job is writing documentation, which it is not in this class, right? So what we care about is, can you implement the features that you need to implement? All right, so just going back to last time, we were in the middle of discussing the process abstraction. And I just want to point out that at this point, we're talking about this container abstraction, the process, and it contains these other abstractions. There's some degree of circularity here that we kind of have to break into. So that's kind of where we are. We will come back and discuss these other abstractions in a lot more detail and how they're created. All right, so any questions about what we covered Friday? We're in the middle of this long, dull example that I will try to wrap up rapidly so that we can move on. All right. So this is where we were on Friday. We were talking about we're talking about a process, Firefox, and the different system resources that Firefox would be using and what it might be using them for. All right? And so what I want to continue doing is just showing you. Now, when you guys set up your environment for assignment 0, whether or not you use Timberlake or whether or not you use our virtual machine, you can actually start doing this stuff. So somebody emailed me last week and they were like, I tried killing some other person's process on Timberlake and it didn't work, right? And I was like, good, that's a good thing. I'm glad, because if it worked, I'd be worried, right? I keep getting the same email over and over again over the weekend, so something's not working properly at UB, but Timberlake is okay. But on your little virtual machine that we're going to give you, you are God. You can do whatever you want. You have unfettered pseudo privileges. So you are welcome to play all sorts of games on that system and fool around, right? So a lot of the stuff we go over in class is stuff you can run on there. Most of these commands are also safe to run on things like Timberlake, although they may or may not be installed. I don't know. Top is pretty common, right? So how many people have used top before? All right, awesome. So you guys know what top does. So let's try to find out a little bit about an example process. So let's look at bash, right? What is bash? Bash is a shell. Bash is not the only shell in the world, but bash is a popular shell. It's the shell I use. A lot of people probably use bash. A lot of you guys probably use bash without even knowing you're using bash because it's installed by default on a lot of systems. So here's one way to find out. So what does this command do? Similar to something that we ran last time. Yeah.
List the processes for a user and then
So this actually will show all the processes on the system that have bash anywhere in the PS output, right? And in this case, there are two processes that have bash in the output. What are they? Yeah.
one is the current shell, the other one is you grepping for.
Yeah. That's the only annoying thing about this way of doing things is that it turns out that if you grep for something, grep finds that thing, right? So there were two commands that had bash in the title. One was my shell, and the other was me looking for my shell. All right. That's how it works. OK, so another way to do this is there are these helper functions on Linux. So pgrep will just do the same thing. It looks for bash. What is pgrep printed for me there? It's the process ID. So these commands are really useful when you're trying to kill things or you're trying to whatever. OK, and then if I just run a bare PS, what it'll do is it'll show me the processes that are running under my user, right? And again, what that shows me here is my shell and the PS command itself, right? OK, God, just said that. OK, so now what we're going to do is so let's kind of fill in a view of bash as a process, OK? So bash has a process ID. So now let's get into some even more fun use of PS. So now what I'm doing is I'm telling PS, what is 5257? It's a process ID of bash that I just found a minute ago. So what this is doing, would anyone like to guess what the output of this command is? So these are, so this is kind of interesting, right? These are the threads, right? So Linux makes this distinction between processes and threads. To some degree, Linux calls everything a task. But what this shows me is any of the threads that are running by bash. How many threads does bash have? One, we would hope, right? I mean, it's not that complicated. So this shows me the user, the process ID, the parent process ID, the scheduling priority, and all sorts of other fun things, right? So there's a lot of output for this command. I would encourage you guys to look over this. You know, these are all examples of metadata about this particular process abstraction that the kernel is tracking for me. So for example, the scheduling priority of bash. That's part of the process abstraction, and it's something that's used when we'll talk later about thread schedule, right, to divide up the resources on the system and enable sort of good multiplexing. OK. So if bash had multiple threads, this view would show them. It doesn't. So bash has a single thread. OK. What's an example of a multi-threaded process? Bash is, actually, I shouldn't, but it's not that hard. Pretty much everything, right? Bash is pretty much the only example of a single-threaded process you could think of. But give me one. Call out one. A multi-threaded process. Firefox, Chrome, browsers, what else? Pretty much anything with the GUI is going to have more than one thread. What about server-side things that would have more than one thread? Web server, that's the answer I was looking for. There we go. So let's check out Apache. This was back in the day when I was young and stupid and still running Apache. But anyway, it's kind of fond memories. Jan 22nd, 2011. So this is Apache. This is my PS command for Apache. This is the command line that it started with. And if I tell PS to print out the threads, look at this. I've got all this information about this particular Apache. It turns out when you start off Apache, at least when it used to start off Apache, it actually creates both multiple copies of itself using fork and a bunch of threads. Right? It's trying to sort of optimize how it allocates resources on the system. What are all these threads doing? Why does Apache have so many threads?
Incoming connections.
Yeah, I mean, essentially you can think of Apache as every time you connect to a website, whether it's Apache or Nginx or anything else, there's a thread that handles your request. It takes the request, figures out what you want, gathers the information off of the disk. In cases where I have to do some sort of dynamic, dynamic work on the page, it runs whatever scripts are necessary to process the page and produce HTML output, and then it ships the output back to you. Right, so that's why you have all these threads. OK, so now let's get to some more esoteric commands. Anyone use pmap before? Oh, there, 1, 2 people. So so all these commands, if they're not installed in your virtual machine, you can install them easily using apt-get, right? So these are kind of fun. What pmap does is it shows me information about the memory that the process is using. This dumps information that the kernel maintains about the mapping between parts of the process's address space, which we'll come back to, and the content. So this is pmap. These are addresses. If you've ever seen a seg fault or something like that, those addresses may look familiar to you. Those are addresses in user space. Anyone want to guess what this is right here? Actually, someone tell me what this is, this first line. So what this says is that Bash has a certain memory region that's 876 kilobytes, that it is mapped starting at this address, OX, whatever the heck that is. And then it's listed as bin bash. What is that? It's Bash's code. This is the binary executable. So now you have some idea of how big Bash is when it's loaded, right? So it turns out, we may talk about this later, these other two pieces also came from the Bash executable, but these are, anyone want to guess what these are? So this is also interesting. Look at these, what do these look like? They look like standard Unix permission. So that first region is marked what? Readable and executable, yeah. So that's a great sign that this is Bash's executable code. The next two parts are not marked executable, but they're also marked as having come from Bash's executable file. So what's in there? Anyone want to guess? One of them is actually marked as read-only. So any constant values that Bash has that are not modifiable at runtime would go in there. And then here are constants that Bash can modify, but they're initialized. So if you have a variable in your program that's initialized when the program starts, it ends up in here. It's not executable code, right? That variable cannot be executed. It doesn't contain an instruction, but it can be modified. So these are sort of constants that Bash initializes when it starts, but then can change over time. What's down here? You want to take a guess? What does this look like? This is the C library, right? And the C library, a lot like Bash, has 3 sections. There's this part right here, which is where the code for the C library is. So again, the C library these days is running about 1.5 megabytes. It's pretty impressive, given everything it does. And then it has a couple of small areas for constants and other things. Now, what about this area? Anybody want to take a area right here? It's marked as a non. It could be heap. I'm actually not sure what it is. I think it's actually heap, right? Because I think the The heap is here. It's possible that the heap would be up here, though. But I think, yeah, I think I printed this out because I think that's heap. And then what's down here? It's pretty obvious. This is memory that's being used by Bash's thread for its stack, right? And it turns out the stack is 132K. It's probably not using all of that. That's probably the amount that's been allocated for its stack. I would hope that Bash doesn't regularly get to a stack depth of 132K. That would be a little scary. All right, any questions about PMAP? So now, again, looking down, using these tools that are provided for us that inspect state about the system, I'm now able to fill out more of my view of Bash as a process. So it has one thread. Here's its address space. It's got a heap, a stack, and some code and data that was loaded from the file. I left the shared library out of here. That's, it's a minor detail. OK. So let's run. Oh, I don't know why that's sad. I gave away the punchline of the slide. So LSOF, what does LSOF do? How many people have used LSOF before? So LSOF will list open files. It's pretty cool, right? Now, there are 3 files open here by Bash. What are these? Anyone have any idea? Yeah, up in the corner. Yeah, so these are my terminal, right? That's a terminal device over there. And Bash is using the terminal to read input, my typing, and to display output from things through standard air and standard out. So I also, my little note here is about this. So these are character devices. I also cheated and I added one device here. Let's just imagine that we caught Bash when it was reading its startup file. This isn't what actually happened. This is me doctoring the slide. And of course, Bash typically doesn't have any files open, right? Because it's just reading input from the character. So I was sad, right? This is what you do when things don't work out the way you want them to, right? The night before and when you're writing your lecture slides. OK, so again, let's just imagine that you caught Bash when it was reading. Now, clearly, Bash does read Bash RC at some point. It just reads it, processes it, and then closes it fairly quickly. So this would be hard to catch Bash doing this. OK. So now let's imagine it has this open file. So now, these are the 3 parts of the system we talked about. We have an address space, we have a thread, and we have some files that the process is using as well. OK. So you might be wondering, how does TOP, how does LSOF, how does PMAP, how do they obtain this information? Right? This information is about this process of abstraction, which is created by the operating system kernel. And the way this works is kind of clever. So Linux-type systems, and I think this dates back to early Unix systems, share information about processes that are running on the system through something called the proc file system. Has anyone ever poked around in proc? So when you guys get your VM set up, do this. cd into /proc. It's at the root. It's normally mounted at the root of your file system hierarchy. And proc behaves like a file system. So you can change into it. You can list things in there. There's all these directories in there. You'll find all sorts of stuff in there, right? Now, what's cool? Oh yeah, check this out. So I can, for example, I can list this entry. What is proc 7615? What does that contain information about? Process ID 7615, right? So the proc directory is organized where there's a subdirectory for each process that's currently running on the system. And so you can see there's all sorts of stuff in here, right? Here's the command line it was started with. Here's information about the environment. Here's the executable that it used when it loaded up. What else? Here's something about its stack. Here's information about where it's waiting in the kernel, if it's waiting for something to happen. So this is essentially TOP. All these tools use this information to generate their output. All TOP does when you run it is sits in a loop, reading this information, displaying it in a nice, pretty format, and then sleeping for a second, right? What's cool about this, just to finish up this example, is that proc is not a real file system. There is no files, there's no disk blocks that store this information. It's all an illusion created by the operating system. But it's a nice solution, right? Essentially what it allows is user programs to read information from quote unquote files that's maintained by the kernel. So when a process is created, Linux will create a new pseudo file in this directory, which allows things like top to find out about it. So anyway, it's kind of neat. Yeah. Because there's no need to store this information on disk, right? And in fact, maintaining proc, so you could write the contents of proc to disk, right? But you'd actually generate a lot of unnecessary disk activity, right? Like, who cares? So there's no need to store this. There's no need for this information to persist. When you shut the system down, how many processes are running? 0. So proc is empty, right? Yeah.
What happens when you sleep? Like, where does it go?
Well, if the computer is sleeping, there's no way to access this, right? So it's pretty much, it's a good question. I suspect that Linux maintains some information in memory about what should be in here. But essentially, when you open stuff in proc, all that's happening is Linux is saying, aha, he opened proc whatever, I'm going to make it look like a file, right? It's a file, it's what's called a file-like object. It behaves like a file, looks like a file, smells like a file, acts like a file, reads and writes like a file. There's some things you can't do in proc. You can't move stuff around. That would be bad, right? Like if I could move a proc entry from one place to another, that would be strange. But in general, proc behaves a lot like a file system. It's a great question. So it's very cool. Gives you a sense of the kind of illusions, the kind of tricks you can pull when you are the operating system. OK, so let's review a little bit. These are the core abstractions we're talking about. We sort of walked through the process of figuring out how they work out in real life. We talked about some examples, and we've also shown how you can find out information about a process using standard command line utilities. And again, file-like objects are things like proc that behave like a file. When we come back to talk about files, what we'll say is they obey the file interface, right? It's kind of a neat idea. And some parts of the file interface, but they actually don't reside on disk. OK, so I'm just going to skip the review today because we're a little bit behind. OK, ooh, wow, there's lots to review. OK. So now, do you guys have any questions about the core process concept? The slides are going to be up on the website eventually, so all the stuff will be there for you guys to review. OK. So now, as we go on and we talk about the system calls that allow processes to be created, allow processes to communicate with each other, there's one small change we have to make to this mental model of the process that we built up that's kind of critical. Seems a little like a sort of a minor detail when we get started, but it's actually kind of important, right? So here's what we came up with. We had this model of a process. It has an address space, threads, and open files, okay? And the model here is that the process has sort of a direct reference to this underlying file object. Whatever sort of file abstraction is maintained and created by the kernel, the process has a direct reference to it. And instead, what we're going to do is introduce what's called a level of indirection. Has anyone ever used or playing around with the standard Linux sort of Unix file interface, things like read, write, open? OK, so you guys have seen this in action, even if you didn't know what you were experiencing. So it turns out that processes don't have a direct access to this underlying file object. Instead, what they do is they map. They have a table that's maintained. It's called a file table, and that file table maps to these file handles, which then map down to file objects. So here I have this direct reference of the file object, and here what I have are this level of indirection where I have essentially a pointer to a file handle, which has a pointer to an underlying file object. Now we'll talk about this a lot more. But the idea behind a file handle, so if you guys have used things like open, what does open return? When I use like, and not like Python open or something that's fancy and returns all sorts of beautiful things, but what does like open, the C library open return? Yeah?
File descriptor.
And what is that file descriptor? Yeah, so what's returned by an open is actually an int. It's an integer. And that's also what's passed to read, to write, to identify the file that you're modifying. So that int allows the kernel to look up the file handle in a table that it maintains in the kernel for that process. Okay? So I map file descriptor, which is an int, to a file handle, which is a kernel object, to a file object. And then the file object allows me to locate things on disk. So I've introduced what's called a level of indirection, and now I've also made my mapping more complicated, because now I have to go from an int to one kind of object to another kind of object to the actual physical reality, right? The disk blocks that hold information about this file. So why would I do this? Does anybody want to guess? All it seems like is I've created extra pointers that can potentially dangle and cause all sorts of problems. So why? Why would I do this? Yeah.
So you can add all the metadata and like handle what you can read or write this file.
Oh, that's a good point. So, there's a suggestion that this allows me to add extra metadata. I don't think that's actually true, although it could be true in certain cases, because I would argue that that sort of information, the permissions and things like this, belongs on the file object, right? So that doesn't end up in the file handle. When you try to do an operation on a file, the file system is going to check every time to make sure that you have those permissions, right? So it says, okay, does user Challen have write access to this file? If so, I can let this proceed. If not, I air it out, right? But that's actually stored in the file object. So yeah, this is not. This is a cutie. So this isn't done just to make things more complicated, right? And this is, but this technique of introducing a level of indirection is something that we see over and over again in operating system design, and allows us to do a bunch of different things. We'll come back to this when we talk about virtual memory, which is by far the most sort of elegant use of this in operating system design. But one of the things that this does is it allows me to take, so for example, with just the file object, I have all this metadata, and it all has to be placed on the file object. And if two processes have that file object open, they both have to see the same metadata, right? So there's no way to share parts of the metadata differently. By breaking this up into two pieces, what I do is I create the opportunity for certain information about files to be shared between certain processes, okay? The way this works is as follows. The file descriptor, that int, the process's file table is always private to it, okay? So the process file table is not, it's shared by threads within the process, but is not shared by any other process on the system. So if process A opens a file and gets a file descriptor of 10, that file descriptor is meaningless to every other process on the system, or it would just refer to some other file if that process had 10 files open, okay? Now, the file handle object, which is the next level indirection, is normally private. So when I create a new file object, when I call open, what happens is a new file handle is created that's private to me, okay? And then the file objects, I'll come back to that middle bullet. The file objects themselves are maintained by the kernel. So those are shared among all processes. Now, at first, it doesn't seem like we accomplished anything here. But what's interesting is the file handles can be shared between two processes. And this is the way that a lot of really important IPC is done on Unix-like systems, including pipes, okay? So how does this work? So when, let's see here, right? So what I'm trying to do here, right, is separate policy from mechanism by adding this level of indirection, right? So now what I can do is I can apply a different type of policy to certain information about the file. So I'm going to allow file sharing between two certain processes under some very specific conditions, okay? So any questions about this? I know this is a bit elliptical right now because we haven't talked about fork. But once we talk about fork, this is going to make a lot more sense. But this is an accurate view of the world, right? Any questions about this? You guys are going to understand file handles and file descriptors very well because you're going to actually have to implement them to complete assignment 2. All right. So now let's start talking about the process lifecycle. This is probably something that we'll go through Wednesday, if not Friday. Okay, so there are 4 key system calls that you need in order to maintain processes, right? So the first thing that you have to do is create a new process, right? So if I couldn't create new processes, I'd be stuck with whatever process is created by the kernel when it starts up, right? So fork is the Unix system call that's used to create a new process. Anyone ever called fork explicitly? Okay, a couple people. That's cool. And by default, now, on modern Linux systems, there are a gazillion variants of fork. Fork takes all these arguments and can do all sorts of different things. So essentially, what we're talking about is the simplest possible version of fork. This was kind of the original version of fork. And again, now if you want to, you have a lot more control over what gets shared by fork. But the easiest way to understand fork is that fork creates a process that is an identical copy of whatever process called fork. So fork allows me to create a clone, right? I thought I had an animation of that, okay? So after fork is called, we refer to the caller of fork as the parent. And assuming that fork completed, parent has now created a new child. Does this make sense? Any questions about fork? OK. So what's that?
Is there any sort of relationship between the new process and the fork process?
Yeah. We'll come back to that, right? So the reason why we call the parent, yeah, sorry, I'm just let me slow down a little bit. So the reason why we refer to the parent and the child here is because there are certain things that the parent is allowed to do, right? And there's a certain relationship that's established between these two processes, right? There are system calls that the parent can make to do certain things for its child, and there are certain things that are shared between these two processes initially. Does that make sense? Yeah. So yes, the answer is yes, okay? So in general, again, fork tries to make an exact copy of the process that created it. So when you call fork, if you're bash, and bash calls fork, which it does, yeah.
Will the file table be same?
Yeah, let's come. Let me get to that in a minute. Yeah. So fork is going to make a copy. And so again, if I am bash and I call fork, what I get is a brand new copy of bash, right? Now that's usually not what I want, but we'll get back to talking about how processes change. But this is essentially kind of the canonical way that a shell would work, right? When you run a command, the first thing the shell would do is create a new copy of itself, and then that copy runs the command that you execute, okay? Now again, if you look at the man page for fork, there are 1,000 different options now that can control sort of what gets copied. But for the purposes of this class, just assume that fork tries to make an exact copy. Now, the only exception to this is when a process has multiple threads, okay? So threads and fork are difficult to work out together, okay? So here's the problem. Let's say that I have 10 threads in my process, and the process calls fork. How many threads in that process called fork? One of them, right? And so that means the other 9 really have no idea what's going on, right? They don't understand that there's about to be a fork that takes place. And more importantly, sometimes those threads have state in the kernel that's very difficult to, well, actually, so there's one obvious problem here, right? Which is I'm making a copy of the process. How do I ensure, let's say the process has 1 thread. What's nice about fork that allows me to create an exact copy of the process? So I've got 1 thread in my process. It calls fork. What else is happening in that process at that point? Is anything about the process going to change while the fork is running? Probably not, right? Because in order for it to change, something in the process has to execute, and the only thread of execution in the process is in the middle of calling fork. So the nice thing about fork when there's only 1 thread is that the fork system call can assume that the process is kind of quiescent, right? There is an internal state that's changing. Because when I make a copy, I want the copy to be consistent, right? It needs to be a copy that's sort of a stable moment in the process's execution. And when the thread is calling fork, I know that if there's no other threads in the process, that nothing else is happening. So that's a good thing. Now, if I have multiple threads, what's the problem? What's that? You're a mumbling answer. Speak up.
I was thinking, so this thread, I have no idea what other thread is.
So what could that mean, right? So those threads generally don't understand what's going on. So let's say I'm trying to copy the process, and copying the process takes a little bit of time. There's a bunch of memory pages I have to copy. The problem is that while I'm doing that, these other threads are executing. And so what might happen is I get like a copy of the left hand of the process that doesn't quite match the copy of the right hand of the process, right? Because they were kind of in the middle of doing something, right? So this creates a lot of problems with calling fork and trying to create a new copy of a program that has a bunch of threads. And the typical way of fixing this problem is just to ignore it, kind of, right? So if you call fork with a process that has multiple threads, the only thread that gets copied is the thread that called fork. So, in practice, if you want to fork and then create a bunch of threads, normally things like Apache will fork first and then create the threads afterwards, right? Because if you create the threads first in fork, you lose all those threads that you just created. OK. Got it. So instead of trying to copy all of the threads from the process, we're only going to copy the thread that actually called fork, right? OK. So fork copies one thread. Fork copies the address space. Fork copies the OK, so this comes back to your question. So fork is going to copy the process file table, right? Now, remember that the file table is, again, internal to the process. What is in the file table? So the file table is this array. The file descriptor is an index in that file table. What does that file table contain? I can back up a little bit if we're missing the diagram. There's some things on these slides. OK, so here's my file table, right? What's in the file table? Pointers to file handles, OK? So if I copy the file table, what is the child process going to have? Pointers to file handles. What pointers to what file handles? The same file handles as the parent, right? So let me try to, No, I give up. There's no marker. OK. So if you imagine I've got one file table here with some pointers to it. I make another copy. I've got pointers now to the same objects. Right? Yeah. I'm good. I'm good. Yeah, I just did it in the air. You guys can't see that? I can see it. Anyway. Yeah. OK. So yeah, oh, there we go. Check that out. OK, there they are. They decided to show up. I was wondering if they would, right? Yeah, exactly. I conjured them up, right? Now you can see them, right? I'm not crazy. OK, so yeah, so I've got one process. I've got my parent. I'm going to make a copy of the thread that called fork to thread 1. I make a copy of the address space, and then I copy the file table, right? So this is kind of interesting. We went back to saying, is there this special relationship typically between the parent and the child? And here is that an aspect of that special relationship, which is that the parent and child can, if they want to, share the file table after fork is called. And this is common, all right? And now one of the most interesting things about fork is that fork is a very unique call in that it returns 2 times, right? It's a little weird, right? I mean, typically calls that you make in C do not return twice, right? And it's kind of, fork is in a way the dual of exit, right? Because how many times does exit return? Does exit return? No, 0, right? So exit never returns. Fork returns twice. And by combining those 2 calls properly, I can essentially sort of maintain this invariant, right? Which is that every process is created using fork and then calls exit, right? OK. Fork returns twice. Now what's complicated about that is that fork is going to return once in the parent and once in the child. And if the parent and child didn't have this sort of special relationship, then it wouldn't matter, but they do. And so it's important for the child and the parent to know who they are. And so fork returns twice, but it returns 2 different values. In the child, it returns 0 on success. In the parent, it returns what? Returns the process ID of the newly created process on success. Fork does other things on failure, which this code should be checking for, but whatever. So this is a very common idiom. If you look at code that creates multiple processes, you see things like this, right? Yeah. Is it its own PID or the parent's PID? Well, OK, so remember, if I'm the child, fork returns 0, right? So nobody gets the parent's PID. If I'm the parent, what should fork return? The child's PID or my PID? The child's, right? Because I know my own PID. There's like a system call that will give me my own PID. What I don't know is the PID of this new process that I've just created, right? So that's what fork's designed to tell me, right? The other semantics of fork is that all the contents of memory in the parent and child start out being identical, OK? Now, they are, sorry, that's ugly. And both the parent and child start off with the same files open in the same position, right? Now, the interesting thing is one of the things that's stored in the file handle object is the file offset. So if either the parent or child changes that offset, reads or writes to the file, both the parent and child are going to see that. And this is something that I can use to set up sort of rudimentary communication between the parent and the child, right? OK, so this is another piece of, well, this code you probably could actually run on Timberlake, and it would make people angry, and it would probably lead to an email from Ken Smith or something like that. So don't do that. You're certainly welcome to run it in your own VM, but you should be prepared to have a way to shut it off and turn it back on again. What does this code do? Yeah, so this is what's called a fork bomb. Has anyone ever done this by accident? I've done this a few times. Oh, it's terrible, right? It's like, I mean, it's incredible. If you don't have some sort of limits on your system that will prevent this from just totally crashing the whole thing, it's pretty impressive how quickly this will just totally lock your system up, right? It's almost as fun. We had a student leave my lab a few years ago. We were shutting down one of his machines, and we decided to see what would happen if we did like sudo rm-rf/, right? And it ran for a while. I don't think it even completed. We got bored. We were hoping that it would blow up or something, but it didn't. All right, so that's my fun fork slide. All right. So on Wednesday, we'll keep talking about the rest of the process lifecycle. Stay tuned for an email this afternoon. Please start looking at assignment 0.